metabolite, which is a major metabolite. So that is piroxicam. Again, we are saying the metabolism is structure dependent. The meloxicam, you have this methyl group here, which is highly susceptible, and therefore undergoing omega-1 hydroxylation to give us that. And of course, that can change to the carboxylic acid glucuronic conjugation, and of course, the minute that those things happen, then the drug will be highly water soluble and readily removed from the body. So we have said it's extensively aromatic hydroxylation. That's where were we first? Yeah, due to the differences in structure. And then we are saying piroxicam is extensively metabolized in humans. The major metabolites in humans resulting from cytochrome P450, hydroxylation of the pyridine ring, and subsequent glucuronidation. Other metabolites are less important. Aromatic hydroxylation at several positions of the aromatic benzothiazine ring may also occur for a minor metabolite, but this is what we call the major metabolite. Dehydration gave a tetracyclic metabolite, which the saccharin or the known metabolites of piroxicam lack anti-inflammatory activity. Related oxycam undergo different routes of metabolism depending on their structure. For example, pseudoxycam, the N2-thiazole analog, undergoes primary hydroxylation of the thiazole ring, just like meloxicam, followed by ring opening, whereas isoxycam undergoes primary cleavage reactions of the benzothiazine ring. So the metabolism are structure dependent. I only stressed the two which are more popular. Oxycam's drug interactions. Concurrent administration of aspirin has been shown to reduce piroxicam plasma levels in the body. So if you give aspirin and these drugs, you see these drugs, as we have said, almost all of them have albumin. They will shown to reduce piroxicam plasma levels. Could be because, could be solubility, because if you give aspirin, it's an acid, and this other one is an acid, so the solubility of one will be affected. I should think so. Concurrent administration of aspirin has been shown to reduce piroxicam plasma levels. The anticoagulant effect of acenocoumarine is potentiated presumably as a result of plasma protein displacement. Of course, all these drugs have plasma protein binding, and therefore they will always give us drug interactions in terms of, because of plasma protein binding. Sometimes they can give you interactions, as I have said, because of solubility, because if we are giving two acids, the one which is more soluble, which will go more into solution than the other one. Because if you look at piroxicam, the aspirin is more soluble than the piroxicam. Remember, for every drug to get to the site of action, even within the circulation, it first must go into solution. That is always the first step. It must first go into solution. It must be soluble within the aqueous solution, even if it's in the blood. Goes into solution, and then when it goes into the solution, undergoes an equilibrium, the less ionized is absorbed, whereas the other one remains unabsorbed. So all we are saying, most probably when you give aspirin and piroxicam, aspirin has higher acidity, it will precipitate, or it will give lesser plasma concentrations in terms of solubility. It will reduce the solubility of piroxicam in the blood, and therefore definitely reduce its activity. It is readily absorbed on oral administration. It is usually given as a once daily dose. Single daily dosage is possible. Again, used for management of arthritis, pain, fever, and inflammation. It is, as we said, has preferential binding. I don't want to call it selectivity. Preferential binding for the COX enzyme, but that is lesser than what you have in the coxibs, celecoxibs, which we are going to mention. It is when administered orally in the highly bound plasma protein. It is extensively metabolized by, again, cytochrome, the cytochrome, the microsomal enzyme, or the cytochrome P450 enzyme, and we have said through the thiazole, the methyl group, through oxidative hydroxylation of the methyl group that is found in the thiazole ring. And I think with that, I'm done with the of the enolics, but unless if there is any question. So that's the first class of the enolics. We'll go out into the market. We are only looking at the different types of the non-steroidal anti-inflammatories that you find. And of course, the choice between one and the other will depend on many variables. You see, you might prefer to give piroxicam because it's a once daily. It has, of course, lesser acidity than compared to the indomethacins, ibuprofens, and so on. So you have a wide choice from which clinician may choose, or even for this, most of these drugs, they're even given over the counter. But do remember, they can also cause a lot of toxicity, especially if somebody is highly susceptible to ulcers and they take some of these drugs, they will get a lot of gastric irritation, If we do not have any question, then we move on. So we are done with the first category of enolics. As I said, under the enolics, we have two classes. We have the oxycams, and we have the pyrazole and pyrazolidine dione derivatives. The paraminophenol, no, it's not there. Paraminophenol, that is paracetamol. You study it much later. So when we look at these drugs, this is a pyrazole. Pyrazole is a ring where the two nitrogens are adjacent to each other, and then it has unsaturation. So it has two nitrogen adjacent to each other, and then 3 carbon atoms with unsaturation. We talk about the pyrazole where there is unsaturation. Pyrazole, there is unsaturation, sorry. Unsaturation in pyrazole and saturation in pyrazolidine. So that is the difference between the two. And then the pyrazolidine dione is where, again, you have these two oxygens. The oxygens are usually in position 3,5. We usually call them the 3,5 pyrazolidine diones. Pyrazolidine diones. So if you consider, usually call them position 3,5, you consider this position 1, 2, 3, 4, 5. So 3,5 pyrazolidine diones. Diones because of that oxygen and that oxygen. That's usually position 3 and 5. If you look at that drug, there's something very, very clear that we can see that we do have a position here. This carbon here has 2 hydrogens. And neither of those hydrogen can be acidic. Either of these hydrogen can be acidic. And that hydrogen can be acidic because of the fact that 2 oxo groups or 2 carbonyl groups, do remember these carbonyl groups, these oxygens pull away electrons. And once that oxygen pull away electrons, it creates an electron deficient. An electron deficient or an electrophilic carbon here. This electron deficient carbon here now will also pull away, pull hydrogen electrons, and therefore this carbon here will have hydrogens that are very readily, can be very readily lost because of the pull of the electrons from these 2 oxygens, pull of electrons from those oxygens adjacent to each other, creating highly electrophilic carbons, and those carbons again will pull electrons, and therefore the hydrogens which are here will be readily lost, and once they are lost, they will be lost as protons, making this compound acidic. So these oxygens, the adjacent oxygens, are very, very important in enhancing the acidity of this hydrogens at that position. But it is important to note that these pyrazolidinones, the pyrazolidines, and even the pyrazoles are actually basic in nature. They are basic in nature, but with an acidic hydrogen. Basic in nature, but with an acidic hydrogen, because when you look at them, you can see this nitrogen has a lone pair of electrons, that nitrogen has a lone pair of electrons. So indeed, this position here again can act a Lewis base by donating electrons. It can act as a Lewis base, and a Lewis acid can come for those electrons. And once a Lewis acid comes for those electrons, then, or when it acts as a Lewis base, it can be able to attract a proton, and therefore this position here will act, either of these nitrogens will act as a base, but that does not remove the point that it has an acidic hydrogen. It has a hydrogen which is being created by the fact that you do have the pull of those electrons. Now, when you also look at this, there's acidic hydrogen. So if you lose that one of those acidic hydrogen, those electrons, and we are losing it as a proton, those electrons of that acidic hydrogen can come in and that can move you out. So again, these pyrazolidine or even the pyrazolidines and the pyrazoles, but mainly the pyrazolidine diones, because the pyrazolidine diones, because of that oxygen, again, have an ability to exhibit ketoinotautomerism. Remember, ketoinotautomerism is the ability of a group to either exist as a ketone or an amino or as an alcohol. And this is the basis of the non-steroidal activity of these drugs. The fact that they can undergo ketoinotautomerism, and in undergoing ketoinotautomerism, they can be able to exhibit acidity. Again, they will have an anionic charge. That anionic charge is necessary for these drugs, again, to bind the receptor, which is cationic within the COX enzyme. So some of the examples, the pyrazole, we have the antipyrine and aminopyrine. We look at antipyrine again, this one has one phenyl substituent at that position, 1, 2, 3, 4, 5, and one carbonyl group. Again, that carbonyl group pulling the electrons. Here you have a hydrogen. So if this hydrogen is lost because of that pull, then that can come here, this coming here, that pushing it out. So therefore, these drugs have also ability to exist as ketoino, can undergo ketoinotautomerism, and therefore have acidity properties. They are assumed mainly to block or to inhibit the brain COX enzyme, not really the periphery, but they do have some activity. So antipyrine is a prototype, and its antipyrines were discovered by accident. Aminopyrine is an analog, more potent and longer acting, but both possess significant incidences of blood disorders. They both possess significant incidences of blood disorders, mainly a granulocytosis. They do bring about a granulocytosis, and therefore they are not in much use. When you have a drug that has a serious toxicity, like a granulocytosis, what is a granulocytosis? Pharmacology. Mimi niishia kitambo sana. What is a granulocytosis? So they cause blood disorders, and which can be fatal, namely a granulocytosis, and therefore they are not popular. They will not be much used. In fact, you will find in most countries they are actually banned, or they are obsolete, or they have been withdrawn from most of the markets because of those toxicity. So you have we have the antipyrine, the aminopyrine, and then you have the dipyrone. The dipyrone is just a derivative of the aminopyrine. If you look at your aminopyrine has this nitrogen CH3. So one of these methyl groups is derivatized. That methyl group is derivatized with the sulfonic acid, and once it is derivatized, you can see CH2SO2ON. So it's just derivatization of one of that to give us a dipyrone. But these drugs it is a prodrug, and in the body again it will be cleaved to give us the aminopyrine, or even further to give us the antipyrine, which indeed are the ones which have activity. So that is a dipyrone in the body, which to be cleaved to give us the aminopyrine. And then you also have this, which we call the dichlorofenazone, and all this is gyrine. You can see this is a structure of antipyrine condensed with chlorohydrate. This is the structure of chlorohydrate with antipyrine. Again, by virtue of the fact that we have said this will generate an anion, because of this pulling electrons a lot, there will be some delta positive. So these can be condensed together. They give us the dichlorofenazone. It doesn't have any much added advantage. It's only like chlorohydrate. This chlorohydrate is known to cause sedation. Indeed, it is even given to children when they are undergoing some certain stressful maneuvers, when they're undergoing stressful maneuvers, then you can give them chlorohydrate. So that is just combining two drugs. One causes a bit of relaxation and sedation, whereas the other one is a non-steroidal anti-inflammatory, of course, antipyretic, and an analgesic. So to try and see whether you can. So it's a complex aminopyrin and chlorohydrate. It is a common agent in many OTC analgesic. It is a mild sedative used in migraine, tension, headache, and of course the sedative effect is because of the chlorohydrate. Doubt it's aminopyrin. This looks like antipyrin. So it's a complex, not amino. It's a complex of antipyrin. This is antipyrin and chlorohydrate. And as I have said, chlorohydrate is also a sedative hypnotic. Those were the first drugs, but as I have said, quite good. They have good effect in terms of pain and antipyretic effect, and also non-steroidal anti-inflammatory. But they were also associated with several toxicities, especially the blood disorder, granulocytosis. And I asked you, what is a granulocytosis from your pharmacology? What is a granulocytosis from your pharmacology? What's a granulocytosis? Granulocytosis. What is a granulocytosis, class? Hope you can hear me. Can you hear me? Can you hear me? Granulocytosis. Mmekimya, kwani mmepotea? Katigila mnakimya mpaka mwalimu anashindwa kwamba bado mko. What is a granulocytosis? That is from, you must have mentioned that terminology in pharmacology. What is a granulocytosis from your pharmacology? You must have mentioned it. I believe. I hope you have. Let's. A granulocytosis, any informed answer? Oh, low white blood cell count, decreased production of granulocytes, low granulocyte, yes, which means it will cause a lot of infections, yeah, because we do not have the white blood cells are the ones which fight, the ones which are responsible for fighting in the body, so therefore person will be highly susceptible to infections. So they can cause that granulocytosis, and therefore, as I have said, not very popular drugs. And because of that toxicity found with these drugs, and yet we have said the activity and paralytic and analgesic activity was discovered by chance. The chemists tried to work on them to see whether they could produce another molecule which had lower toxicity and still maintained very, very good activity. And so that's what, again, you have said, search for better drug, produce the pyrazolidinediones, which are acidic because of the beta diketone tautomerizes into the acidic kino. So we are starting from there, and then we come to this drug, and that's the drug we are saying undergoes ketoinotautomerism very well, and therefore better activity. And out of that, we have the phenylbutazone. Phenylbutazone, again, if you look at this drug, we are saying it's position number 1, position number 2, 3, 4, 5. 3,5 pyrazolidinedione, 3,5 pyrazolidinedione, and at position number 4, you can see the best group that was found for anti-inflammatory activity was found to be an N-butyl group. N-butyl group, not branched, was found to give us best activity. Again, you can see at this position, you have a hydrogen. You have an acidic hydrogen, just as we said about the pyrazoles. You do have an adjacent to oxo groups, or two highly electron withdrawing groups, and therefore that hydrogen there highly acidic, and the electrons can be lost. And once those electrons are lost, I mean, there are protons, sorry, not electron, a proton can be lost. And once you lose a proton, that is those electrons coming in this way. And as they come this way, then that tautomerizes, and we had already shown to give us ketoino tautomerism. And therefore the phenylbutazone agrees with the need for an acidic group. Again, if you look at all these drugs, if you look at this oxygen when it becomes a negative, if you count the atoms that separate the anionic site with either of these, with the first, considering that we can consider this to be our first, hydrophobic group, and this is here our anionic site. We did not mention that you always must have carbon atoms. You can have atoms, so you can't count. If this is our anionic site, this time, of course, it's not a carboxylic site. It is a hydroxyl group through ketoino tautomerism. Then you can count that as our first carbon, and you can count that as our second atom. So we still are in agreement with the rule, which we had said, that the anionic site is still being separated from the first hydrophobic group with two atoms. They are not necessarily carbon atoms, and I don't think we didn't mention we need to stress carbon atoms, but we are saying the anionic site is still separated from the first hydrophobic group. You have that hydrophobic group, you have that second hydrophobic. So the first, the anionic site is separated from the first hydrophobic group with two atoms, with retention, of course, of activity, because that is a necessary SAR. We have also said the other SAR with these drugs are obeying is that, of course, we are saying they have an anionic site which is developed through ketoino tautomerism. Of course, you can also see that these drugs are having what we call our first hydrophobic group, and they also have a second hydrophobic group. Again, these are things that we said are necessary. We do require different hydrophobic centers. Again, therefore, there is structure. Although the structure looks very different, there is still some structural similarities between these drugs and the ones we have already looked at for anti-inflammatory activity. These drugs are able to tautomerize into enols, which in turn ionize at physiological pH, and they still have an aromatic ring with an ionic charge 2 atoms away, as I have described. That will be O minus, 1 atom, 2 atoms, and that is our first hydrophobic center. So they still obey some of the requirements for an anti-inflammatory activity. If you look at, so we have two, there is the phenylbutazone, and then you have the oxyphenbutazone. The oxyphenbutazone is a metabolite of phenylbutazone, in that it is phenylbutazone having undergone oxidative hydroxylation at the para position. That's the oxyphenbutazone. And both drugs, both formulations of both drugs are available in the market. Again, this drug was still found to have some toxicity, still blood disorders, and it can only be used when none of the other safer anti-inflammatories is effective. So you can only go for it when none of the others which is within in the market is available. Characterized by the 1-RL 3,5-pyrazolidine dione structure, which that the presence of a proton which is situated adjacent to electron withdrawing carbonyl groups renders these compounds acidic. So they do have an acidic, they can't be basic in nature because of the nitrogens, but they will still have an acidic proton, and that acidic proton is what we require so that these drugs can undergo ketoino tautomerism. Oxyphenbutazone is a hydrolylated metabolite of phenylbutazone, and phenylbutazone is metabolized in the liver to para-oxyphenbutazone 1 metabolites. SARs, the pharmacological activity of the 3,5-pyrazolidine dione derivatives are closely related to the acidity, the acidic hydrogen at 4 position. In other words, you abolish that acidity and you lose your activity. So that's why we are saying they are closely related to that acidity, in that you require an acidic proton there for their activity. The dicarbonyl functions at 3 and 5 position enhance the acidity of the hydrogen, and of course they are enhancing that acidity because of their electron withdrawing ability. Eliminating the acidic proton at the 4 position abolishes anti-inflammatory activity. That is very important because, again, and we understand why they require to exhibit ketoinositol, give us the anionic charge, be able to bind on the cationic site within the COX enzymes. Without that, they will not be able to bind the enzyme. Enhancing the acidity too much leads to a decrease in anti-inflammatory activity while gaining other effects like uricosuric effects and sodium retention. Again, what is uricosuric effect? Uricosuric effect. And all we are saying, if again you make this group here too acidic, in other words, it's also a very potent electron withdrawer, the drug reduces in its anti-inflammatory activity and it acquires other activities as uricosuric activity and also sodium retention. So in other words, it retains sodium. So it becomes a mineralocorticoid. It retains sodium. The single alkyl group at the 4th position enhances anti-inflammatory with the most activity being given by N-butyl substituent. So that substituent is not there by mistake. The N-butyl in phenylbutazone and in oxyphenbutazone. It is there because it is responsible. It was a group that was found to be responsible for maximum activity. We have said when you put a group which is too acidic, phenyl ethyl group at the 4th position produces anti-gout. So I already asked you, what is uricosuric effect? Uricosuric effect is where you increase the uric acid loss. You increase uric acid loss, that is uricosuric effect. And therefore, if you increase the acidity of that group too much, like here you can see you have this group again is electron withdrawing, and therefore this drug, the sulfenpyrazone, you can see it is structurally the same. It's a 3,5-pyrazolidinedione. Just 1 minute. Look at that drug. All we are saying, it has structural resemblance with the phenylbutazone and even the oxyphenbutazone. The only difference is this group here. So this group, change of this group can give other activities, but when it is retained as N-butyl, which gives us the maximum activity, that drug has good anti-inflammatory activity. It's marketed as an uricosuric. The 2 phenyl rings are not coplanar due to their close proximity on adjacent to the alpha hydrogens, each are effective. The ortho hydrogens, hydrogen one, each are effective at this. So they are not, the two. So what we are saying is just like we had said before about non-coplanarity, not coplanar. Again, a requirement for these drugs. So these phenyl rings, which are here, these phenyl rings, they show non-coplanarity, and all we are saying is the hydrogen. Remember when we talked about hydrogens, and these hydrogens in hydrogen at this position, hydrogen at this position, those hydrogen, remember they are surrounded, although they have only 1 electron. That electron can introduce steric hydrons, that 1 electron, that other electron, and therefore this throw each other. So just as required for activity, again, these 2 hydrogen show non-coplanarity. This oxygen responsible for what we have said, ketoinositol, and hence the drug obeying some of the rules, might not obey all of them, but obeying some of the rules, and therefore exhibiting non-steroidal anti-inflammatories. It is equipotent with antipyrin and more potent than aspirin for treating inflammation. It has a long half-life, but it has serious toxicities, just like we have said, of the antipyrin, e.g. granulocytosis, peptic acid, bone marrow depression limits is used in long term. So you find that this drug, in fact, you will only be given as a last resort, that you do not, there is no other drugs. You have tried all the drugs on a patient and none is working, and therefore you do not have any alternative, and that's the only time you can use it. It's active it's metabolite. The oxyphenbutazone is also an active metabolite, similar. It is less toxic, and it also has a shorter half-life. It's better tolerated. Omega-1 hydroxyl is an omega-1 hydroxyl metabolite, another metabolite with uricosuric activity, but lead to anti-inflammatory activity. The keto metabolite, those are just the metabolites that you can have of N-butazone. So you have this omega -1 will be a metabolite at that position. Omega -1 will be there. Omega will be at that. If you get omega -1 hydroxyl group, you can also get the keto metabolite. And we are saying those metabolites, but the major metabolite, as we have said, is the para-hydroxyl metabolite, but you can have others, as we have said, hydroxylation at that position, oxidation at that position to give us a ketone, but they have almost insignificant activity. The one which was found to have as a metabolite is the oxyphenbutazone. The keto metabolite Kebuzone is marketed in Europe as a uricosuric agent. So we are not interested. We are not discussing the uricosuric agents. We are discussing mainly the non-steroidal anti-inflammatories, and therefore we are saying phenbutazone and its para-hydroxy metabolite oxyphenbutazone have good anti-inflammatory activity. But as we have said, they have also been associated with toxicities and therefore not very popular. The oxyphenbutazone, you have said, is a little bit safer, but also still having toxicities. And that when a drug has serious toxicities, that limits its use. That you limit its therapeutic use, because once you use it, then you can also you're also exposing that patient to serious toxicities, and therefore they can get a relief fever and the inflammation, but you introduce another disease. Like if you're talking about depression of the bone marrow, then you can also introduce a plastic anemia, and now you will have a lot of problems. So those are drugs that one has to use. They are reserved drugs. You can only use them when the patient has no choice. They are still in it. Whether, either way, you look at the benefit, the risk-benefit ratio. You look at the risk-benefit ratio and then make an informed decision whether indeed the patient should have the drug. I think with that, again, we are done with the pyrazolidinediones and the pyrazolones and the oxycam. So we are done with the enolics.